This is a double integral polar equation. We're trying to find the area enclosed by the curve r of theta is equal to 4 plus the sine of theta plus the cosine of theta. The graph is provided for you, sort of a deflated circle, and we do this as a double integral where we radially slice outward from the origin. The ends of that slice are the r bounds, and then we spin this in the direction of increasing theta for the theta bounds, or they can just give it away and tell us that theta is equal. Theta goes from 0 to 2 pi. So we have the theta bounds from 0 to 2 pi. When it comes to the r bounds, we'll go from 0 up to the curve. 4 plus sine theta plus cosine theta. When you're doing an area with double integral, there's a 1 in the integrand, and you have your choice of whether you want to do that as dy dx, dx dy, or if it's circular in nature, r dr d theta. The extra factor of r comes from the Jacobian. And so for us, we'll have r dr d theta. Integrating r, we get r squared over 2. And we have to evaluate that from 0 up to this 3-part function, 4 plus sine theta plus cosine theta. Then later we integrate from 0 to 2 pi. And so what we're going to end up with is 1/2, pull that on the outside, and it's our job to square this 3-part 4 plus sine theta plus cosine theta. So what I've done here is I've written it out in a nice 3x3 grid, and anytime any row or column crosses each other, that's when you multiply. And so we'll have a 16, a 4 sine theta, a 4 cosine theta, a 4 sine theta, a sine squared theta, a sine theta cosine theta, a 4 cosine theta, a sine theta cosine theta, and then finally a cosine squared theta. That gives us our 9 parts of the product. And so, as far as numbers go, we'll have the 16 together with this sine squared plus cosine squared, which is 1. And so that'll give us 17. These two guys equal to 1. And so we have a 17 here. Combining the 4 sine thetas, we'll have 8 of those sine thetas and 8 of those cosine thetas and 2 of those sine theta cosine thetas. Okay. And we just proceed from there. Doing our antiderivative, we'd have 17 theta. We'd have minus 8 cosine theta. We have plus 8 sine theta. When it comes to this last one, if you think of just a quick u substitution, letting u be equal to sine theta would be the best choice, because du is directly the rest of it, cosine theta d theta. So you'd be looking at the integral of 2u du, and that's going to be u squared. And so we'll get sine squared theta as the antiderivative of that. You also can use an identity on this one too. This is exactly the sine of twice theta. And so we plug a 0 in, we plug a 2 pi in, and we'll end up with the following. The half is on the outside still, and so we have a 34 pi minus an 8 plus an 8 plus nothing, and then we'll have a 0 minus an 8 plus nothing. Wait, I'm sorry. Back up 1 second. The 8 sine theta evaluated at 2 pi is a 0. And then plus nothing. So what happens is these 8's cancel out, and all these zeros are what they are. You end up with 17 pi for your answer. Okay. Also, you could have skipped the integration of these two guys, well, even the third guy too. Once you recast it as the sine of twice theta, you could skip the integration of all three of those guys. Because of the way sine theta works, when you integrate from 0 to 2 pi on it, the positive area and the negative area cancels out. The integral of sine of x from 0 to 2 pi is guaranteed to be 0. Same thing works for cosine x in a different way, because we have it looking like this, where these positive areas cancel with these negative areas. So we didn't have to really integrate those. We could have just said that we're integrating a full period of these two guys. And when you integrate a full period of a sine or cosine, you end up with 0. Even if it's the sine of twice theta, the period on that is going to be pi. So you'll be integrating 2 full periods of that. And so we could save ourselves some work and not have to worry about integrating when we integrate a full period or multiple periods of integer multiple periods of sine or cosine of twice theta or 4 theta, and so the period on cosine of 4x is pi over 2. The period on cosine of 2x is pi. The way you get the period is you take the old period and you divide by the multiplier. If you're looking at the cosine of nx, the period on it is 2 pi over n. And so this is done by the time you get to pi. So if you're ever integrating from 0 to pi on the cosine of 2x, you get 0. Even if you go from 0 to 2 pi, you'll get 0 because it'll be 2 full periods. And so for here, this is 2 full periods. This here, from 0 to pi, that is 2 full periods of cosine 4x. And you don't have to worry about doing that integral. Okay? Alright, great. Comment below if you have any questions.